Ellipses and circles.
by Dana Alhajaj.
Raghad Omar.
and Waajd Siddiq.
Firstly, our objectives for this lesson are to acknowledge how ellipses relate to science, use equations to help identify ellipses and circles, apply our understandings to solve, and lastly, analyze and graph these equations. In physics, we learned that Kepler's first law states that the paths of planets are ellipses, with the sun at one focus. The figure presented is slightly exaggerated to convey the path Earth takes to orbit. Earth's actual orbit is nearly circular. In fact, it has an eccentricity of 0.00167.671.
An ellipse, resulting from the intersection of a cone by a plane in a way that produces a closed curve, is a plane curve surrounding 2 points, such that for all points on the curve, the sum of the two distances to the 2 points is a constant. For instance, an ellipse can be made by putting 2 pins into a cardboard and a circle of string around them. Then, putting a pencil in the loop and pulling as far as possible in all directions without breaking the string. Foci are the two fixed points in an ellipse. The major and minor axes are both perpendicular segments passing through the center, with the center as the midpoint. The major axis contains the foci and has the vertices as the endpoints. It is essentially the longer axis, while the minor axis has the co-vertices as the endpoints and is the shorter axis. The aforementioned vertices are the endpoints of the major axis, and the co-vertices are the endpoints of the minor axis. Eccentricity determines how circular or stretched an ellipse is. It is the ratio of c, the distance between a foci and the center, to a, the length of the semi-major axis. It always has a value between 0 and 1. When the eccentricity of an ellipse reaches 0, it becomes a circle, a special type of ellipse formed by the perpendicular intersection of a cone by a plane. It has only one focus. There are two different equations for the horizontal and vertical ellipse. Both equations share the same numerator, so the denominator is the determiner of the type of ellipse. In the equation, a is always greater than b, so when under x minus h squared, it denotes a longer horizontal line and subsequently a horizontal ellipse. Likewise, when a is under y minus k squared, the formula indicates a longer vertical line and a vertical ellipse. However, both equations have the same center, hk, and ABC relationship with c equaling the square root of b squared subtracted from a squared.
Since the foci and vertices lie on the major axis, the x and y coordinates change for either horizontal or vertical ellipse, respectively. Similarly, the co-vertices vary, the y-coordinate for the horizontal ellipse and the x-coordinate for the vertical one since it lies on the minor axis. Following the same logical pattern, the horizontal line y equals to k is the major axis for the horizontal ellipse and the minor axis for the vertical ellipse. This only leaves the vertical line x equals to h as the minor axis for the horizontal ellipse and the major axis for the vertical ellipse.
The first equation we have is graphing an ellipse. X plus 4 squared over 9 plus y plus 3 squared over 4, which equals to 1. To determine which type of ellipse you have, either a horizontal or vertical, look at your a value. A is always larger than b. If the larger number is under the x squared, the ellipse is horizontal. From looking at this equation, h equals to -4 and k equals to -3. Radical a squared equates to 3 and radical b squared equates to 2. And derived from the ABC relation, we can get the c, which equates to 2.2. Because the ellipse is not located at the origin, the center is h and k, which is -4 and -3. The foci is h plus or minus c and k, which is -1.8 and -3, and -6.2 and -3. The distance between the vertex and the center is a, so the vertices is h plus or minus a and k. which is -1 and -3, and -7 and -3. The distance between the vertex and the covertex is b. So the covertex is h, k plus or minus b, which is -4 and -1, and -4 and -5. The major axis equals to y equals -3, and the minor axis is x, which equals to -4. The second question is writing an equation for the ellipse with these characteristics. We have the two vertices and the two foci points. Because the y coordinates of the vertices are the same, the major axis is horizontal, and the standard form of the equation is x minus h squared over a squared plus y minus k squared over b squared, which equals to 1. To get the center, you have to do the midpoint formula, which is 3 and -3. H is 3 and k is -3. The distance between two vertices is 2a. So 2a equals 20 and a equals to 10. So a squared equals to 100. The difference between the two foci is 2c, which is 16. So c equals to 8. To get b, we use the ABC relation formula. So b equals to 6 and b squared equals to 36. The equation of this ellipse is x minus 3 squared over 100 plus y plus 3 squared over 36, which equals to 1.
Astrophysicists have discovered a minuscule spherical object orbiting the Sun and have decided to label it as Planet X. As they continue to study it, they have determined that the object's eccentricity is zero point 0.3. If the object has a width of 10 meters, what is the height of the object? First of all, we know that eccentricity equates to c over a, so the using the ABC relation. Oh my god, I'm so sorry. So
Using the ABC relationship.
using
So using the formula, we can obtain C, which equates to 3. Next up, we can derive B from the ABC relationship. Accordingly, 3 squared equates to 10 squared minus B, and after solving, we conclude that B equates to 9.5. Because the height is equal to 2b, we multiply our answer by 2, and thus the height of said object is 19 meters. Thank you for your
thank you for
time.
your time.
People retell